as you know, I mean, these days everyone uses, mobile phones, which has again touch. Without touch, I think these days it's difficult to operate any of the
That's true.
equipment.
You don't have buttons anymore.
Yes, yes. So, yeah, we were talking about the touch. So, how that works?
Yeah,
Maybe
how does
briefly
that-
we can. So, I mean, we know human body is made of mostly water.
Yes.
So I think 60% or 70% is, and
Bit of salt.
yes,
Some
yes,
electrolytes. And,
yeah. So it's a little bit conductive and has some dilatory property also. So and capacitance equation you have mentioned, parallel plate used is epsilon 0 epsilon r a by d. Of course, I mean, you can have two electrodes like this and then introduce the finger here, but that's not the way the touch works.
Right.
I mean, this will be impractical to use.
Exactly.
But on the other hand, let's say you have two electrodes. It can be in different forms. Let's say I have one electrode here, which is excited using some sinusoidal signal. And let's say I have, this is a cross-sectional view, another surrounding electrode.
Okay.
So what I'm trying to draw is, I have one layer here, if I look from top, then I have not the best drawing, but I have another outer layer.
Right. So this is planar.
Yeah, this is planar.
Yeah.
Right. And the center one, let's say, is excited at ground. Sorry, excited using Bs. And let's say the outer one goes to is maintained at ground.
Okay.
Right. So that means, as you have explained earlier, there will be electric field lines from this to this. Correct.
Correct.
There will be more electric field lines, but these are some of the pictorial view of electric field lines. Provided the outer one is connected to ground, they are falling on the outer one. Now, I can actually measure by maintaining this at maybe a virtual ground. Let's say I'll introduce a feedback impedance here.
Like a follower or something.
Yes, ZF, and I get an output as a function of the displacement current received by this receiver electrode, which is in surrounding. So maybe I'll call this as the transmitter electrode and this as the receiver electrode.
Okay.
So I'm getting some output. Now, let's say we introduced our finger here. Yeah, let's say.
Let's say there's a finger.
Yeah. So what will happen?
Well, that finger is connected to ground, right? Through us. Is that correct? To assume that? Or is that just a finger?
We can consider both cases. So one thing, so what you're saying is, this guy is standing on the floor.
Yes.
He is capacitively actually connected to ground.
Yes.
And when you're standing there, there is maybe, depending on the shoe that you're using, there is some ground capacitance here, maybe a couple of hundreds of 100 to 150 picofarad. And then let's say like this. So actually, depending on the distance between the receiver and transmitter, right? Now let's say you are just entering into the, so let's say the finger is somewhere here.
Yeah, because you
you're
From the
going
top,
close
yeah.
to it.
Yes.
So definitely, as you pointed, some of the field lines which were otherwise landing on the receiver will now stop with the finger, like we have discussed earlier,
Yes.
right? And this current will go to ground.
Which current?
The current which is received by the finger
Ah, it will go down. Yes.
will go to ground.
Yes.
So I will not be getting it here.
No.
The receiver current which I was receiving earlier will reduce. So that means, let's say, with without finger, let's say I was getting some output here. With finger, I will have a reduction.
Yes. But it will still keep it at that level.
Yeah.
Yeah.
So now you can decide. See, when you have this electrode arrangement, this will also be, protected using some insulator, etc. You can decide the thickness and so on.
Right.
So if you want the mode to be like this only, in the sense some amount of shielding has to happen and then output has to reduce, I will say, okay, this is finger.
Right.
Right. Presence of finger.
Right. But that shielding should be low as possible if you want to be more sensitive, I guess. I mean, the height of that shielding, I guess.
Yeah. So that depends on the the electronics. See, now here we have shown just an kind of I2V converter.
Yes.
If you have better and better instrumentation to measure smaller and smaller capacitance values, you will be able to even see finger coming couple of centimeters away.
Okay. Yeah.
Now the other question is, let's say I move the finger very close, as close as this. Not a great finger, but
Yeah.
it looks like some device. But yeah. So now also there will be shielding current going through this.
Probably more. Is it?
It will be there. But what we have observed is, since you are very close to it, now there will be a lot of current going in this way also. So it's like you have two electrodes and then you have kept a dielectric material which has high permittivity.
Yeah.
So water is 80 epsilon r.
Yes, pretty high.
Yeah.
Compared to air.
Yeah. For the water approximately. So it's a very good medium for the electric field. So this, we would say, the coupling effect can be dominant compared to the shielding effect.
Right.
So when you are very close, in fact, the output can go up. So the designer has to come up with ways to distinguish these two. One way is to look at the leakage current, I mean the current that is leaking to ground, and then make use of that alone.
Leaking to ground through the person.
Yeah. Or what I would say is, see, there is some amount of current going from the transmitter. If most of the current is received by receiver, they will be almost equal.
Yes.
Correct. Now, when you bring in hand, due to the shielding, the current received by the receiver will reduce.
Yes.
If you have a way to measure that difference, it will show how much is leaked to the ground.
Okay.
So the measurement mechanism can be in a way that you measure that leakage alone somehow.
Right.
So then it is as a function of the shielding alone.
Right. I mean, ideally in this situation, if you're talking about smartphones, for example, you don't want the button to be pressed when your finger is far away. Because,
Correct.
So you actually want to at least slightly touch it.
Yeah. Right. Now the distance that we are talking is a function of many things. I mean, depending on the electrode size, how far they are, what's the surface area of this. So it's not something we can calculate using this.
Yes. It's not so straightforward.
Yes. So usually people do, also it's mostly for consumer electronics applications. So you will have constraints. Okay, this is the space that you have. I also need to view it. That should not be
exactly,
affected.
Or even if you hover your hand over it, it should not make any difference, right?
Yes. So all those are considered while designing. What we are discussing is just a touch switch.
Oh, yeah. Okay. This is a capacitive
This is
touch
just
switch.
a touch switch. I mean, instead of a press button,
Yes.
I just show my finger, it just detects.
Right.
Utilizing the permittivity of the finger or utilizing the leakage current.
Yes.
Right. The other way, what you are talking is, if it's
sorry, Babu, the capacitive touch width. What are some of the examples that you would use? Where would you use a capacitive touch switch?
See, we might have seen even in some of the coffee machines, etc. You will be just touching your finger.
Yeah.
I mean, there are optical ways to detect, but there are also capacitive ways to detect.
So that's an example of.
Yes, that's an example. And there is no moving part in this. So the lifetime will be more.
Right.
But if you have a mechanical switch, after some press, it will die. So since you mentioned about the display, I mean, this can be extended to, let's say I have, two wires like this. They are not touching each other. One, there is some gap between these two.
Okay.
So there is some capacitance that is formed between these two.
Yes, in that region.
In that region. So if you put your finger there, it will change.
Yes, correct.
Right?
Technically, it should change.
Yeah. So it can be made use of to see whether your finger is present or not.
Okay.
Now this line can be so thin that your view will not be affected. Right. Now I can have many of this. And form a grid depending on the spatial resolution that you want. So I will be getting such capacitance values in all these intersections.
So that means your app, let's say you are clicking on app, is in between them, correct?
So this gives you let's say these are the excitation points. I may measure excite one by one and measure from this side.
Right.
So I will know which capacitance has changed. I know the location. Right. Now you are talking about a finger that covers two nodes.
Yes, I'm talking for example.
Yeah. So I think it doesn't stop with just measuring capacitance. There will also be certain algorithms to take care of such mischiefs that we do.
I see. Right.
So this capacitance information goes to a control algorithm.
Some intelligence is
there. Intelligence system that looks at, okay, this could be the most appropriate and then decide. And see, your finger is not that small.
No.
So, you don't need grids of, what shall we say?
You don't need fine grids.
Yes, we don't need fine grids. Yes. So the gap between this two can be reasonable.
Yeah.
So you just have to see,
Maybe that's why if you have like a small animal land on the app,
it won't. Correct. So the touch switch, from the touch switch, we can extend this to the actual capacitive sensor used for the display, touch displays, correct? It's called as touch display or
touch display, right?
Yeah. Whatever our mobile phone.
So not just mobile phones.
What do you hear? Yeah.
Even computers, laptops, TVs.
Yes.
Right. I guess they all.
Nowadays, everything is coming with
touch, right?
Yeah. So that's a huge industry, and.
But based on capacitive principles.
Yes.
Yeah. Very nice.
So it has got unlimited applications. So, as we said, low cost. But some challenges are like, let's say you dip this whole thing in the water. Then it will just smile at you. I mean, or if there is humidity, high humidity present,
Right.
then these measurements can get affected.
Right.
So that is one challenge it has. See, even here, let's say there is some amount of accumulation of water in this region, then these readings will change.
Yes. What about EMI?
EMI, see, this will not be sensitive to, what shall we say, the magnetically induced or if there is a DC magnetic field or even time varying magnetic field, it may not have much effect other than the induced voltage in the wires and so on.
Right.
But if you have, let's say, electric field which is interfering with this, then it can get affected.
Correct.
So then what you do is the excitation that we have talked about here, and then the output that we are receiving here. I mean, we know, is it from, let's say if this is at F and if this is not at F, then you know it's an interfering frequency.
Right.
So at that time you can switch to a different frequency. So there are ways to reduce the effect of such interferences. But as you said, interference is a problem because these electrodes are, particularly the touch based electrodes, are open. It's not shielded.
Right.
Because it has to see your finger, so it's
Exactly.
not shielded. And in fact, 50 Hertz interference is a problem.
Oh, right.
Because I mean, when you have touch switch here, like I've drawn, and then if you have a wire going away nearby 230 volt, 50 Hertz.
Should be some electric field.
Yes. There will be parasitic capacitance from this to this.
Yes.
And then the circuit I have drawn here will show up output due to this also.
Yes.
So we will have to come up with ways to reduce. I mean, since here the electrode is open like this, you cannot avoid it, but you will have to use some filters and so on to get rid of this effect.
Because that 230 volt, that's a kind of fixed.
Yeah.
Depending on the distance.
The 230 volt, 50 Hertz,
230 volt.
if that is fixed. Yeah. Yeah. If that is fixed. So see, now you have computer wires and so on. One day it may be like this, next day it may be something.
That's true.
Yeah. So by design, our electronics should be able to handle such interferences.
Right.
So there are plenty of applications. I think students, if you are interested, they
it's
should look at.
unbelievable, I think, the number of applications for capacitive type
Yes.
sensors. Yeah, I think we've covered quite a bit.
Correct. Correct.
Right. I think especially when it comes to the human body,
Yeah.
right? There are also lots of things inside the body that you can measure
Yeah.
using these capacitive principles,
Yeah,
which we did not see with magnetic fields, right?
Yeah.
So
In fact, there is something called capacitance tomography, as you know,
right.
where, I mean, if you have a cross section of the tube like this, and if you can have electrodes surrounding, and then if you can make all these measurements, you will be able to see. I mean, sometimes we see, let's say, a half-filled pipe and so on, and part of it may be air, part of it may be petroleum products and so on.
Right.
So how do you how to know how much of it is petrol or
Right.
some fluid, liquid, and the other air combination or ratio.
Right.
So the permittivity is different. So from these capacitance measurements, people do inverse calculation and see how the permittivity is distributed inside the pipe.
Right.
So capacitance tomography is one such approach where you can get this kind of information about permittivity distribution, which is also, as you said, can be extended for human body. There we may not call it as capacitance tomography, but it may be called it as impedance tomography.
Right.
Because it's not just capacitance, permittivity alone. Human body is also a bit conductive.
Yes.
So both effects will come.
Right. Yeah, I mean, there are really very interesting applications. Even for, I read that if you have, let's say, a certain amount of bacteria or something that you take from the body, and you want to look at its growth rate, you could still have a capacitive sensor.
Yeah.
So when it grows, right, your permittivity is somehow.
Yes.
So a lot of medical
Yeah.
applications.
So
too.
there the electrode size, etc., will have to be very tiny.
Very tiny. Yes.
So maybe microfabricated and so on.
But I think that's one of the advantages, is that it's easy to fabricate this.
Yes.
Large scale or small scale.
Yes.
So-
Yes.